Hello students. Welcome back to class. Today, we'll be exploring simple AC circuits, part 3. But before we begin, let's quickly review what we covered in our previous lesson. In our last class, we learned that capacitive reactance is the opposition a capacitor gives to alternating current, as seen in devices like radios, televisions, and power supplies, while impedance is the total opposition to AC in a circuit, combining both resistance and reactance. Our lesson objectives today are: first, we are going to explore phase. Then, we will discuss power in an AC circuit. Phase refers to the state of vibration of a system that varies periodically, at a particular moment in time. It is usually expressed as the angle, omega t, also called the phase angle. In alternating current circuits, the concept of phase describes how one sinusoidal waveform relates to another. There are three main cases. First, in phase. When the phase angle is 0 degrees, the waveform peaks align perfectly with the reference axis. Mathematically, this is written as A of t equals am sin omega t. Second, positive phase. If the phase angle is greater than 0, the waveform is shifted to the left. This means the signal leads. The expression becomes A of t equals am sin of omega t plus phi. In this case, the peak occurs earlier in time by phi over omega. Third, negative phase. If the phase angle is less than 0, the waveform shifts to the right. This means the signal lags. The expression is A of t equals am sin of omega t minus phi. The peak is delayed by phi over omega. In summary, a positive phase angle means the signal leads, while a negative phase angle means the signal lags. The magnitude of the phase angle tells us how much time shift exists between the signals, calculated as phi divided by omega. In an RLC series circuit, the phase difference between the applied voltage and the current is determined by the circuit's reactance and resistance. The relationship is expressed as tan phi equals X over R. Here, X represents the net reactance, given by XL minus XC, while R is the resistance of the circuit. In an alternating current circuit, power is the rate at which electrical energy is transferred or converted into another form, such as heat, light, or mechanical work. Unlike in direct current, where current and voltage are always in phase, in AC circuits the current and voltage may not align. This means we need special consideration to calculate power. The average power consumed in an AC circuit is given by the expression P equals I times V times cos phi, where I is the effective or RMS value of current, V is the effective or RMS value of voltage, and phi is the phase angle between voltage and current. Cos phi, also called the power factor, shows how much of the power is truly useful. If the circuit contains only resistance, the power absorbed is given by P equals I squared times R. This represents the true power converted into heat in the resistor. I is the current and R is the resistance. We are solving a problem on an AC series circuit. A coil has a resistance of 400 ohms and an inductance of 0.8 Henry. It is connected to an alternating voltage supply of 24 volts, RMS, at 60 Hz. We are asked to find the current flowing in the circuit, the voltage across the inductor, the phase difference between voltage and current, the average power consumed, the potential difference across the resistor. Solution. We are given resistance equals 400 ohms, inductance of 0.8 Henry, frequency of 60 Hz, voltage supply of 24 volts. Step 1. Current in the circuit. The inductive reactance is given by the formula 2 pi times frequency times inductance. That is, 2 times pi times 60 times 0.8. This equals 301.6 ohms. Impedance of the circuit. The total impedance is the square root of the sum of the resistance squared and the reactance squared. So, the square root of 400 squared plus 301.6 squared. That is, the square root of 160,000 plus 91,000. which equals the square root of 251,000. This gives 500.96 ohms. Current in the circuit. The current is voltage divided by impedance. So, 24 divided by 500.96. This gives 0.0479 amperes, or 47.9 milliamperes. Step 2. Voltage across the inductor. This is current multiplied by the reactance. So, 0.0479 times 301.6. That equals 14.45 volts. Step 3. Phase angle. The tangent of the phase angle is reactance over resistance. That is, 301.6 divided by 400, which equals 0.754. Taking the arctangent gives a phase angle of 37 degrees. Step 4. Average power consumed. The power is the current squared times the resistance. So, 0.0479 squared, multiplied by 400. That equals 0.918 watts. Step 5. Potential difference across the resistor. This is current multiplied by resistance. So, 0.0479 times 400, which equals 19.16 volts. Final results. Current, 47.9 milliamperes. Voltage across inductor, 14.45 volts. Phase angle, 37 degrees lagging. Average power, 0.918 watts. Voltage across resistor, 19.16 volts. Congratulations on completing this lesson. You should be proud of yourself. Let's put your memory to the test with a few quick questions. Today, we cover two important areas. First, phase. Then, we discuss power in AC circuit. Thank you.